Section. Introduction. We're going to delve into the world of large multimodal models, LMMs, such as GPT-4V, Ision, and Gemini, which have demonstrated impressive abilities in understanding and reasoning about visual and language-based tasks. These models have primarily been trained using content from the web. However, an often overlooked aspect of the web is the websites themselves. Each website is visually designed for easy human consumption, which presents both a challenge and an opportunity for LMMs. Consider screenshots of websites, which can contain thousands of elements with intricate relationships. These are more complex than the images typically used in benchmarks, which are usually focused on specific objects or scenes. But if LMMs can accurately understand websites, it could open up a multitude of applications on the web. Our goal in this work is to explore the potential of LMMs as generalist web agents. A generalist web agent, as defined in the Mind2WEB project, is expected to follow natural language instructions and complete tasks on any given real-world website. These tasks can be quite diverse and complex, sometimes requiring more than 10 actions across multiple dynamically rendered web pages. Previous work has primarily used large language models, LLMs, like GPT-4 on raw HTML input. However, HTML code is noisier and less information-dense than the rendered visuals. For instance, a screenshot might contain 423 HTML elements that would require 186,490 textual tokens with the GPT-2 tokenizer, while only needing 1,445 visual tokens using GPT-4V's visual tokenizer. Moreover, HTML alone doesn't provide complete information and misses critical semantics from embedded images. To address this, we propose SEEACT, a generalist web agent that leverages the power of LMMs for integrated visual understanding and action on the web. We'll focus on GPT-4V, the most advanced LMM currently available, and compare it with smaller LMMs like Blip2. We find that GPT-4V is highly capable of visually understanding rendered web pages and generating the right plans in textual forms across a wide range of websites and tasks. However, grounding, or converting the textual plan into precise actions on the website, remains a significant challenge. This involves selecting the right HTML element to interact with and the right operation, like click, type, or select. We propose several grounding methods, including superimposing bounding boxes and index labels onto the image, similar to set of mark prompting that has been shown effective on object or scene-centric images. But we find that on complex images with rich semantic and spatial relationships like web page screenshots, GPT-4V often hallucinates. The most effective grounding strategy uses the known correspondence between HTML elements and their visual rendering, a unique property for websites compared to natural images. We evaluate SEEACT on the Mind2WEB dataset and compare it with text-only large language models, LLMs, like GPT-4 as well as smaller models, FLAN-T5 and Blip2, specifically fine-tuned for web agents. In addition to the standard offline evaluation setting on cached websites, we also establish an online evaluation setting by developing a new tool that allows for running web agents on live websites. Our major findings are as follows. SEEACT with GPT-4V is a strong generalist web agent, if Oracle grounding is provided. In online evaluation, it can successfully complete 50% of tasks on different websites, substantially outperforming existing methods like GPT-4, 20%, or FLANT5, 18%. This strongly demonstrates the potential of LMMs like GPT-4V for web agents. However, grounding is still a major challenge. The best grounding strategy still has a 20 to 25% gap with Oracle grounding. Among the various grounding strategies, the best one organically leverages both HTML text and visuals, substantially outperforming image annotation strategies by up to 30%. In context learning with large models, both LMMs and LLMs show better generalization to unseen websites, while supervised fine-tuning still has an edge on websites seen during training. There's a non-negligible discrepancy between online and offline evaluation because there can often be multiple viable plans for completing the same task. Online evaluation is more indicative of a model's true performance. In the next section, we'll explain the problem formulation of web agent and then introduce our developed SEEACT, a generalist web agent based on GPT-4V. Specifically, given a web-based task, like rent a truck with the lowest rate on a car rental website, we examine two essential capabilities of GPT-4V as a generalist web agent. Action generation to produce an action description at each step, like, move the cursor over the "find your truck" button and perform a click towards completing the task, and element grounding to identify an HTML element, like, button, find your truck, at the current step on the web page. Section summary. Large multimodal models, LMMs, like GPT-4V have shown impressive performance on vision and language tasks, but their potential as web agents has not been fully explored. In this work, we propose SEEACT, a generalist web agent that combines visual understanding and action generation using LMMs. While SEEACT demonstrates strong capabilities in understanding and generating plans for web tasks, grounding the textual plans to precise actions on the website remains a challenge. However, SEEACT outperforms existing methods in completing tasks on different websites, highlighting the potential of LMMs for web agents. Section. Formulation. Let's break down the given section of the paper into simpler terms. The paper discusses a web agent that is designed to perform a specific task on a website. For instance, if the website is a car rental service, the task could be, rent a truck with the lowest rate. The agent's job is to generate a sequence of actions to complete this task. At each step, the agent generates an action based on the current state of the website, the actions it has already taken, and the task it needs to complete. The state of the website is represented by an HTML document and a screenshot image. The agent's action corresponds to a browser event, which we can think of as a set of three variables: the target webpage element to operate on, the action to be performed on the target element, and any additional value needed for the operation. However, the agent can't directly generate these three variables. Instead, it generates a textual description of the intended action, which contains information about these variables. This process is called action generation. To interact with the website, the agent needs to convert this textual description into an executable action. This is called action grounding. In the action generation phase, we instruct the agent to imitate a human browsing a web page. It analyzes the task, the web page, and the previous actions, and generates an action description based on this analysis. In the action grounding phase, the agent faces the challenge of converting the action description into an executable action. It's relatively easy to derive the operation type and value from the action description, but the real challenge is identifying the target element. To address this challenge, we explore three approaches: grounding via element attributes, grounding via textual choices, and grounding via image annotation. In the first approach, we prompt the agent to generate as many details about the target element as possible. This helps to match the target element with the HTML element. In the second approach, we provide the agent with textual representations of elements as choices to facilitate grounding. In the third approach, we overlay a bounding box for each candidate element and an alphabet label on the bottom left of the bounding box. The agent is expected to generate the label corresponding to the target element. Finally, to assess the performance of action generation, we use an oracle grounding method, which ensures the variables can be identified as long as they are mentioned in the action description. We approximate this method by asking human annotators to identify the agent's intended actions. Section summary. Given a website and a task, the web agent needs to generate a sequence of executable actions to complete the task. These actions are formulated as triplets of variables, E, O, V, representing the target webpage element, the action to be performed, and any additional value needed. However, agents based on language models are typically unable to directly generate these variables, so they generate a textual description instead. To convert the textual description into an executable action, a process called action grounding is required, which involves identifying the target element from the generated description. Three approaches are explored for this: grounding via element attributes, grounding via textual choices, and grounding via image annotation. Section. Experiments. We conducted our experiments using the MIND2WEB dataset, which is a comprehensive collection of over 2,000 complex web tasks with annotated actions. This dataset covers 137 websites across 31 low-level domains, which are further grouped into 12 high-level domains. The dataset supports three main operations: click, type, and select. To avoid confusion, hover and press enter operations are included in the click operation. The purpose of the test sets in this dataset is to evaluate how well web agents can generalize across different tasks, websites, and domains. For instance, the cross-task setting tests the agents on new tasks that weren't part of the training data but are within the included domains and websites. The cross-website setting tests the agents on tasks across 10 new websites for each of the top-level domains in the training data. The cross-domain setting evaluates the agent's performance on tasks in 2 top-level domains that were not part of the training data. Each HTML document in the dataset is matched with its corresponding web page screenshot image from the MIND2WEB raw dump. This is then verified by humans to ensure correct rendering and element visibility. Due to the limitations of the GPT-4V inference quota, our experiments focus on a random subset of 30 tasks from each test split. We provide detailed statistics of these subsets in the tab, subset_stat section. In our methods, we first use the DeBerta base cross encoder from MindAct to rank the top 50 elements for better comparison with its text-only counterparts. Then, we group elements into clusters of 17 options for inference. In grounding via element attributes, no candidate element is provided. We access GPT-4V through ChatGPT Web UI, which only allows a zero-shot setting. To compare with SEEACT, we also implement methods based on text-only LLMs and BLIP2 following the 2-stage strategy of MindAct. First, we use the ranker to pick the top 50 elements. Then, the action generation problem is formulated as a multi-choice question answering problem, with the candidate elements as options, including a none option if the target element is absent. During inference, elements are grouped into clusters of 5 elements, with iterative refinement, until a single choice is made or all options are discarded. We evaluate supervised fine-tuning, SFT, methods using FLANT5 and BLIP2T5 and in-context learning, ICL, methods using GPT-3.5, GPT-4. We fine-tune FLANT5 using a left-to-right language modeling objective with the target sequence of ground truth actions. The fine-tuned FLANT5 then serves as the backbone for inference, enabling action generation in the format defined in EQ, stepwise. The BLIP2 model combines a vision encoder and an LLM with a bridging component for modality connection. We jointly fine-tune the LLM and the bridge module on MIND2WEB training data while keeping the vision encoder frozen. For the vision encoder, we leverage the VIT-L14 pre-trained from CLIP with an image resolution of 2048. To ensure a fair comparison with the FLANT5-based text-only model, we choose FLANT5 as the language model and initialize it with the parameters fine-tuned on MIND2WEB. We also conduct experiments with text-only LLMs, specifically GPT-3.5 Turbo 0613 and GPT-4 Turbo 1106 Preview, using in-context learning in 3-shot settings. We use the same multiple-choice formulation and include 3 demonstration examples for in-context learning as specified in MindAct. For offline evaluation, we use the evaluation metrics used in MIND2WEB. Element accuracy compares the predicted element with the ground truth elements. Operation F1 calculates the token-level F1 score for the predicted operation comprised of action and input value. Step success rate measures the success of each action step. A step is successful only if the selected element and the predicted operation are correct. We report averages across tasks for these stepwise metrics. Success rate measures the success of an entire task. A task is considered successful only if all steps have succeeded. We also conduct online evaluation on live websites to get a better evaluation on the whole task success rate. For this, we developed a new online evaluation tool using Playwright. This tool can convert the predicted action into a browser event. To adhere to ethical standards, our experiments are restricted to non-login tasks in compliance with user agreements, and we closely monitor agent activities during online evaluation to prevent any actions that have potentially harmful impact, like placing an order or modifying the user profile. For a fair comparison between offline and online evaluations, we only rewrite time-sensitive tasks to ensure they are still valid when the evaluation is conducted. For instance, we update the dates for flight-related tasks. Finally, we conduct the online evaluation on a subset of total 50 tasks from the 3 test splits and report the average performance across these tasks. Section Summary. The experiments were conducted on the MIND2WEB dataset, which consists of over 2,000 complex web tasks across various domains. The dataset includes 3 primary operations: click, type, and select, and the evaluation focuses on measuring the generalization of web agents across different tasks, websites, and domains. The methods used in the experiments include grounding via image annotation and textual choices, as well as grounding via element attributes, and the evaluation metrics include element accuracy, operation F1, step success rate, and success rate. Online evaluation was also conducted using a tool that converts predicted actions into browser events on live websites. Section: Offline evaluation results. We found that GPT-4V has the potential to act as a versatile web agent, given an effective action grounding method. We've provided GPT-4V with a human-annotated Oracle action grounding method, which has resulted in a success rate of 65.7%, 70.0%, and 62.1% across 3 different test splits. This method significantly outperforms other models in all metrics across the 3 test splits. It even shows an 11.9% improvement in success rate over the second-best method in the cross-task setting. The advantage is even more pronounced in the cross-website and cross-domain settings, where it leads by 28.3% and 21.2% in success rates, showing its versatility compared to supervised fine-tuning. However, there's a noticeable gap between Oracle grounding and the 3 proposed grounding methods, indicating that grounding, especially element grounding, is a significant challenge. Element grounding via textual choice shows the best performance across all settings, comparable to supervised fine-tuning and showing a substantial improvement over text-only language models. Grounding via image annotation offers an intuitive approach and shows promising results in recent work that focuses on object or scene-centric images. However, we find that on complex images with rich semantic and spatial relationships like web page screenshots, GPT-4V often fails to correctly map its generated element description to the right bounding box and index label in the image, leading to a low element accuracy. This limitation primarily arises from GPT-4V's weakness in understanding image details and relative spatial location. The SEAC choices model demonstrates a substantial performance advantage over the text-only GPT-4 under all 3 metrics across all 3 test splits. It outperforms GPT-4 in step success rate of 8.9%, 14.7%, and 11.2% on 3 settings, respectively. Interestingly, fine-tuned BLIP2T5 does not show a noticeable gain over FLANT5, despite having additional visual input. Several factors may contribute to this. First, the CLIP model used as the image encoder may not be sufficiently adept at image details. Second, BLIP2T5 utilizes an off-the-shelf CLIP model that may not be optimal for web page screenshots. Finally, although the screenshots in the test splits are error-free, some of the examples in the training set might contain issues such as rendering failures or inaccuracies in the timing of screenshot capture by annotators. We compare SFT and ICL methods to offer insights for developing web agents in different scenarios. ICL, with SEEECT, demonstrate consistent and robust performance across 3 test splits. ICL is particularly advantageous in scenarios lacking annotations or requiring strong generalization capabilities for new domains and websites. As grounding methods improve towards Oracle grounding, ICL is poised to show even stronger performance. On the other hand, SFT methods show better generalization across tasks on websites already seen during training. Considering the high cost of data annotation for web agents and the billions of websites on the internet, ICL offers a more compelling solution for generalist web agents. However, if one only needs to develop a strong web agent for a certain website, SFT is still a competitive solution. In online evaluation, we pair a web agent with a human annotator, where the human was tasked to monitor agent actions that may change real-world states and determine whether each task was successfully completed. For comparative analysis, we include success rates from offline evaluation. The whole task success rate in online evaluation substantially exceeds that of offline evaluation. This finding suggests that the whole task success rate is likely underestimated in the offline evaluation due to the variability in actions and plans. In other words, there may be multiple viable plans for a task, but the reference plan in offline evaluation only captures one of them. Across all 3 settings, SEAC choice outperforms both GPT-4 and FLAN-T5 XL, Using Oracle grounding further improves the performance substantially, reaching a remarkable whole task success rate of 50%. Although GPT-4 shows much worse performance than Flan T5XL in step success rate under offline evaluation, they exhibit similar success rates in online evaluation. These results further confirm the potential of large models for generalist web agents compared with fine-tuned small models. We investigate the performance of web agents on tasks across different difficulty levels. We estimate the task difficulty based on the number of actions taken by annotators during action trace annotation. As shown, the whole task success rate is negatively correlated with the number of actions. It decreases as the number of actions increases across all four methods. SEACT Oracle consistently outperforms other methods across all difficulty levels. Interestingly, the gap between SEACT Oracle and SEACT Choice enlarges on longer horizon tasks. This is understandable because grounding errors cascade to later steps. Nonetheless, it further shows the challenge of grounding for GPT-4V and the need for better grounding methods. Section Summary. GPT-4V has the potential to serve as a generalist web agent with the help of an effective action grounding method. The Oracle Action Grounding Method, SEACT Oracle, significantly outperforms other models, demonstrating its generality compared to supervised fine-tuning. However, there is still a noticeable gap between Oracle grounding and the proposed grounding methods, particularly in element grounding, which is a major bottleneck. The SEACT Choices model shows substantial performance advantages over text-only models, and the ICL method offers a more compelling solution for generalist web agents, while SFT methods are better suited for developing strong web agents for specific websites. In online evaluation, the whole task success rate exceeds that of offline evaluation, suggesting that offline evaluation underestimates the performance due to the variability in actions and plans. SEACT Choice outperforms other methods in online evaluation, and the performance of web agents decreases as the number of actions increases. SEACT Oracle consistently outperforms other methods across all difficulty levels, highlighting the challenge of grounding for GPT-4V and the need for better grounding methods. Section. Further analysis and discussion. Let's delve deeper into the analysis and discussion. We'll start with an error analysis in grounding via image annotation. Grounding via image annotation is a method similar to set of mark prompting, which has proven effective for images centered around objects or scenes. However, this method doesn't work as well with complex web page screenshot images that have a lot of semantic and spatial relationships. We took a closer look at why this method fails by randomly sampling 100 predicted actions. We found three main types of errors. 1. Incorrect action generation. 2. Creating a bounding box and label that doesn't exist. 3. Not being able to connect bounding boxes with the right labels. We've included examples of these errors in the section titled Hallucination Examples. Our analysis showed that 53% of the errors came from incorrect action generation, where the model couldn't predict the target element within the action description. This error rate is 27% higher than images without annotation, which have a 26% error rate. This is because image annotation often hides important content within web pages. It's a big challenge to overlay image annotations on web pages without hiding important content, especially because web pages are usually densely laid out with small elements designed for precise cursor interactions. Next, 21% of the errors were due to the GPT-4V model's tendency to misinterpret and fabricate content over the image. Specifically, the target element described in action generation doesn't have a bounding box or a label on the bottom left, where the model is supposed to generate none. However, the model incorrectly assumes there's a bounding box and creates a label as the answer. Another 18% of errors were caused by the GPT-4V model's difficulty in recognizing the relative position within an image. The model can identify both the target element within the bounding box and the labels, but it struggles to connect the bounding box with its corresponding label. Now, let's talk about the GPT-4V model's capabilities. It shows promise in long-range action planning, web page content reasoning, and error correction. It also surpasses the limitations of superficial textual similarity matching that are inherent in fine-tuned, text-only models. The GPT-4V model is capable of long-range planning that involves a series of interconnected low-level actions. It can generate the immediate next step action and also anticipate a sequence of subsequent actions in the future to complete the given task. The GPT-4V model also has the ability to correct errors in previous actions. For example, It can recognize when a mobile phone number is invalid due to the wrong format and generate a description about the action to correct this error. This shows the model's potential for adaptation in online settings, where actions may not always follow predefined, ideal paths as in offline evaluations. The GPT-4V model also has substantial advantages in tasks that require certain knowledge over fine-tuned models at a smaller scale. For example, it can identify the IATA code of the airport in Los Cabos as SJD. Large multimodal models, LMMs, have been developed through large-scale image-text pre-training to achieve in-context learning capabilities. Further work is being done to improve instruction following capabilities with curated multimodal instruction following data and alignment with reinforcement learning from human feedback. GPT-4V and Gemini represent significant progress in LMMs. They have remarkable multimodal capabilities, which include advanced and versatile integration of visual and language reasoning abilities. Their performance on a series of benchmarks also showcases remarkable capabilities on vision and language understanding and reasoning. Web agents are being developed with the goal of achieving seamless human-web interaction. A lot of effort has been put into creating web agents that can understand language instruction and complete tasks on the web. Benchmarks for web agents are being built with simplified environment simulation. Web Arena creates website simulations in the sandbox from 4 popular categories with functionality and data mimicking their real-world equivalents. Mind2Web provides environments in diverse domains, websites, and various tasks on real-world websites by dumping web pages from live websites along with action trajectory annotation. To improve web agent performance, Web Agent pre-trains a T5 model on HTML data and performs instruction tuning to enable long HTML document summarization and action planning. WebGUM enables web agents to observe both HTML and the rendered screenshot by fine-tuning LMM with a large multimodal corpus for web agents. Cog Agent further improves with a high-resolution image encoder to enable the agent to recognize small web page elements and texts. In a concurrent work, GPT-4V exhibits strong performance on mobile UI understanding, which is much simpler than the desktop websites we study. Section Summary. The error analysis of grounding via image annotation reveals that the suboptimal performance on complex web page screenshot images is mainly due to wrong action generation, making up bounding boxes and labels, and failure to link bounding boxes with the correct labels. GPT-4V, a large multimodal model, demonstrates promising capabilities in long-range action planning, error correction, and knowledge-intensive tasks, while also showcasing advanced integration of visual and language reasoning abilities. The development of web agents aims to achieve seamless human-web interaction, with benchmarks and pre-training techniques being used to enhance their performance on tasks in web and mobile UI automation. Section. Visual grounding. Understanding visual details. Despite the impressive vision-language understanding capabilities of language model multimodal, LMMs, particularly GPT-4V and Gemini, they still struggle with detailed visual understanding. Various techniques have been suggested to enhance GPT-4V's ability to understand intricate image details. These techniques usually involve adding visual markers to images, which helps the model to focus on and understand specific areas. Different types of visual markers have been used, including red circles, masked areas, and a mix of circles, arrows, and hand-drawn elements. The SOM method involves dividing the image into meaningful sections and adding an assortment of visual markers such as numbers, letters, masks, or bounding boxes. Training vision language models with data annotated with images has proven to be effective. Cosmos 2 uses text tokens to represent the locations of bounding boxes. Bubo GPT identifies entities and locates corresponding masks for objects in the image. Shikra manages detailed image referencing and understanding by using spatial coordinates as text tokens in both inputs and outputs. Ferret uses both discrete coordinates and continuous features to represent regions, along with a spatially aware visual sampler to handle the diverse spatial characteristics of different shapes. Challenges and potential societal impact. Web agents show great potential for automating everyday web tasks through natural language commands, which could significantly improve web accessibility, especially for those who are not tech-savvy. However, there are concerns and limitations related to the scale of our experiments and safety issues for real-world deployment. Limited experiment scale. Due to the limited inference quota of GPT-4V, we could only conduct experiments on a portion of Mind2Web. We plan to increase the scale of our experiments in the future. Agent safety. While a generalist web agent can automate routine web tasks, enhance user experiences, and improve web accessibility, there are serious safety concerns related to their deployment in the real world. These concerns include privacy issues, such as access to users' personal profiles, and sensitive operations, like financial transactions or submitting application forms. During our online evaluation, we noticed that these web agents could potentially perform harmful actions on the web. We manually checked the safety of all actions before executing them. It is crucial for future research to thoroughly evaluate and mitigate the safety risks associated with web agents, ensuring they are protected against creating and executing harmful actions.